Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we are going to continue this very formal part on database design theory and normal forms. I have a few more things to show you, and then we'll move on, if time permits, to the ecosystem around SQL transactions. So when it's used in the real world with many queries, right? I want to mention, I did it in the email, that the graded quiz is open. Who has already solved it? Almost everybody. So you still have a few hours to do it. I hear that apparently the solutions are shown after the first attempt. So if you still haven't solved it, then maybe that helps you further. That was, of course, an error, but it's no big deal for me because the goal of the quiz is really to motivate you to work during the semester. So the goal is to reward anybody who puts the efforts of learning and trying to understand the material during the semester. The reason for that is that if you learn during the semester, all the knowledge that you learn now is going to be retained in the long term, not just for the exam, but you will also remember in a couple of years what you've learned. So the brain works much better when you learn during the semester. And so this is good for you, everybody who is here in the lecture hall, everybody who is here on Zoom watching live, because you're spreading the knowledge over all of these weeks, so you remember longer. All right. So let's continue where we were. So you remember that I showed you functional dependencies. Who remembers them? Right, very good. Hi, Marcin. So I considered that this is acquired. Then I showed you the super keys, the candidate keys. I showed you the primary keys, which are basically just one candidate key that gets chosen by a human. I showed to you how you can not look at tables. So you can do functional dependencies without even looking at tables. And then you consider sets of functional dependencies. And I showed you that there's all kinds of rules that we can use, like the splitting rule, combine rule, transitivity rule, reflective rule, reflection rule, and so on, right? It turns out that only 3 rules are enough. These are the Armstrong actions. And I give you a bit of intuition on how to read that. Who remembers how to compute the closure of a set of attributes? Who doesn't remember? Okay, most of you remember. So it's this game where you start with a few attributes and you need to use the rules to add more and more and more and more attributes, right? So whenever you have on the left what you know, and you're trying to read on the right what you don't know yet, but you can add because it's a dependency, right? So for example, if you start with A and you have a functional dependency that says A determines B, then you can add B, right? And then if you find another rule that says A and B determine C, then you can add C also, right? And so you grow the bag of attributes until you can add no more attribute, and then you're done. That's the closure of the set of functional dependencies. And then we saw also the tidying up, when you tidy up a set of functional dependencies by trying to get rid of anything that is redundant or untidy, right? So this is what we did on a few examples. I'm going to make you a co-host, Marcin, as soon as you are in the chat. Okay, so we looked at all of that. Are you already in the chat? Oh, really? Are we in the? Did I send the big data link? Could I be in the wrong? That would be. I did a mistake. Which Zoom room is it? Because once I confused with. Does it say big data or does it say information systems for engineers? For 2025. But the people on Zoom here, do you see big data or do you see information systems for engineers? If I'm in the wrong room, no, it is the. I think it is the. Consider name. Okay, because I use the typical one. That's very strange. I sent an email to everybody. Yeah. I have absolutely no idea. What does the link end with that you clicked on? Oh, that's the usual one. To see the number. I would like to see the number. 613. Could it be? Could I be? Maybe. Oh, yes. Maybe that's what happened. Actually, no, I should switch to the other one because otherwise there's people waiting on the other one. Just give me 1 minute. Thank you for letting me know, Marcin. So I will switch to the regular link to where all the people must probably be waiting. So please connect to the other one, and I'll be there in a minute. I am adding everybody. All right. And Marcin, I'm making you a co-host. All right, so welcome back, everybody. So Marcin noticed I was using the incorrect link. I was using another link from another meeting room, but don't worry, you've not missed anything because I was just wrapping up what we said last week, saying that we looked at functional dependencies and super keys and candidate keys and private keys, and that we looked at actions for looking at functional dependencies without the need to look at tables. And we also tidied up these, you remember the tidying up, right? That's called the minimal basis, where we try to remove everything that is redundant and not needed. And the goal is to get an equivalent set of functional dependencies that would constrain the tables in exactly the same way, but just more tidy, right? So who is with me on that? Okay, that's what we saw last week, right? That's a lot. And it's all things that you can exercise on your own. And so here, this is why I left you last week. Let me give you the high-level context to make sure you know why I'm doing this. You remember that I showed you at the very beginning of this lecture a table that has undesirable properties. There were all these anomalies, there was redundancy, there was duplicates, and when you update something, then it causes inconsistencies. When you remove a customer, it removes all the products too, and so on. So that was called an anomaly, and I gave you the intuition of the correct way to design tables, which should normally be that you have plenty of tables. You have one table for everything you need, one table of products, one table of customers, one table of orders. At ETH, you have one table of students, one table of courses, one table of attendance, and so on and so on. That is the intuition. So the goal of everything that we've been doing so far is that we take a table that is not correctly designed, basically a big table that does too many things, and the goal is to split it, to decompose it into multiple smaller tables in such a way that things become clean again, that we don't have any anomalies anymore. Who is with me on that? Right? And so the way we are going to decompose the table is to project it in different ways. Right? We are going to project it to many different tables. And so when we project a table in this way with the goal of projecting it to meaningful tables, we need to ask ourselves which functional dependencies survive in the process. For example, I might have a table with all kinds of problems that wasn't correctly designed and that has these two functional dependencies, right? A determines C and A determines B. And we project it to just A and B, perhaps because we think that then we have a table that is meaningful. For example, it's a table of products, it's a table of persons. Who has the intuition that when you do that, only A determines B survives and applies here because A determines C makes no sense. There is no C in here, right? For whom is that intuitive? Right? Very good. So we say that A determines B, survives the decomposition, but A determines C goes away, right? This we don't keep. So you see that we can carry over, we can project the functional dependencies as well. And so then what I showed you last time is that there is a general brute force algorithm to find out all the functional dependencies that survive the projection. And what I told you that you do in that case is that you're basically looking for functional dependencies on A, B, and C, right? If you project from A, B, C, D to A, B, C, you're looking for functional dependencies that only have A, B, and C, right? So what are the possible left-hand sides of such dependencies? Do you agree it's basically the power set of ABC, right? It's empty, or just A, just B, just C, just AB, just AC, just BC, or ABC, right? These are all the possibilities for the left-hand sides, right? Who is with me, right? So we're going to be brute force trying them all. And what we need to do in order to determine then the right-hand side, guess what? We need the closure. if I take all the possible left-hand sides and I compute the closure of these left-hand sides, then I'll get the functional dependencies that survive. For whom is that intuitive? Right? Okay, so let's do it. So first, all the possible subsets, the power sets, these are the 8 possibilities. These are the left-hand sides of the functional dependencies I'm looking for. And then we need to compute the closures. That's the game that I told you last time. You need to add stuff. So you see, for example, if I have A, then I can add D. And since I have D, I can add B, right? And then I end up with A, B, D, but not C, because C is anyway never on the right. So there's no way I could ever have C on the right if it's not already on the left. So I just compute the closure of this, the closure of this, the closure of this, the closure of this, and I just put them on the right. Who is with me? Right? Now we're reusing what we saw last time. And then we need to get rid of what's not ABC. So D we don't care about because we projected it away. D is no longer in the projection. So we remove D. We don't mind. We don't care about D anymore. And this is what we have. And the next thing we do is we tidy it up, right? We compute a minimal basis, right? So let's tidy it up. What can we tidy up here? Do you spot a few things? There are some obvious ones, right? What can we remove? Yes? Yes, this one we can get rid of. Somebody on Zoom says B determines B, also we can remove. Anything else we can remove? And there's a microphone, by the way, that we can use for the room. So that's more practical. Okay, so we can get rid of this. We can get rid of this, right? So we compute the minimal basis. So empty set also, we can get rid of this. A gives A, we don't care. We can remove A here, right? Because it's redundant anyway. B gives you B, we get rid of it. C gives ABC, we already have C on the left, so we can remove it here. AB also goes away, right? That's trivial. AC gives ABC, then we just keep B because A and C we already had on the left anyway. BC gives ABC, I can remove B and C because we already have them anyway. And ABC gives ABC, we get rid of it, right? Can we continue to tidy it up a little bit? What can we still do? Anybody spot something we can remove that's still redundant? Yes? Yes, why can we remove that? Exactly, we already have A implies B. So A and C, you don't need C basically. This is what it says. A alone is enough to know B, right? And somebody on Zoom also says that we can remove indeed AC gives you B, right? I did, by the way, I told you that because we're in Switzerland and we like things tidy, we split the thing so that we have only one on the right. We like to do that too, right? But anyway, we remove this one indeed because A alone is sufficient to know B. So this is useless. This is redundant. Anything else we can remove? We can remove 2 things. Yes? Why? Exactly, C is enough to imply A, so we don't need this one anymore. We don't care that we also know B. And one more we can remove. Yes? Yeah, what is the name for that rule? Does anybody remember the name? Transitivity, exactly, that's transitivity. And somebody on Zoom also said we can remove for the same reason C implies B, because C gives us A and A gives us B, right? So with these two, we already know that C determines B, right? Who agrees? Right, that's the transitivity, right? The friends of my friends are my friends. So we can remove this, and now we have tidy things up. So you see, it's very brute force, right? That consumes a lot of CPU to do these things. But once you have done it, then you have the projection. And now we have that what is preserved from projecting the table to ABC, what is preserved from everything that was in here is this. That's basically it. Okay. So now we can take it over when we project. And this is now the set of functional dependencies that I have in here. Okay. But again, I told you the goal is to decompose a relation. We're going to take a bad relation, that is too big and does too many things, and we are going to project it on different subsets in order to get something better. So let's take an example of relation. I have ABCD, and imagine that I'm going to project it on AB and on ACD, right? By the way, when I project it, they should overlap, right? Because if I just project it on these joint subsets, then that doesn't bring me anything, because we need to be able to join them back in a way, right? So I project on AB, and I project on ACD, right? And that gives me the projection on AB is right here. By the way, I should eliminate duplicates, right? So you see, this is a duplicate, so that becomes A1, B2. Who is with me, right? And on the right, we project to ACD, and here there's no duplicates to eliminate, right? So you see, we are reusing many things. We're reusing now also the relational algebra, the projection, pi that you remember, and so on. Okay. So basically, whenever we have a relational table and we find two subsets of attributes that overlap, ideally, and whose union is all attributes of R, because we don't want to lose attributes, right? They should be in at least one of the two tables. So we can decompose R into the projection on the attributes in S and the projections on the attributes in T, right? Who is with me? Right? And so if we keep decomposing and decomposing and decomposing and decomposing, we'll get 2, 3, 4, 5, 6 tables. We'll get plenty of tables. So this is what we're attempting to do right now. But we need to do it wisely, because I could just pick sets of attributes a bit randomly and decompose, and that's it, right? But that's not how it works. Who actually could maybe guess one of the criteria under which this is a good decomposition? What should it fulfill? Otherwise, I just continue and I will tell you on the way. I just want to see if somebody spots that already. Can you guess what condition there should be between R, pi s of R, and pi t of R? On Zoom, nobody? All right. I will tell you that. We'll see. But we just do it step by step. Okay. So you remember that I told you about the first normal form. Who remembers that one? First normal form, right? That's, you can't have a table in a table in a table in a table, right? Everything is flat. You can only have atomic values. When I'm going to give you another kind of normal form called the Boyce-Codd normal form. And I will be able to describe that normal form thanks to what I taught you last week. So the idea is that I have a table. I have functional dependencies. And I can infer some of them. For example, if I have AC, what is the closure of AC? Anybody? What is the closure of the set of attributes AC, given this? What can you add? Yes? B and D. So we have ABCD, right? What can we say about AC because of this? What is AC? It is it determines all attributes, so it's a. What do we call that? When a set of attributes determines everything, it is a. Yes? Somebody says super key. So we have minimal basis, we have super key, and we'll do a poll on that. Anybody else? Minimal basis? Okay, so let's do a poll. I would like to see what AC is. AC is a set of attributes. So who thinks AC is a minimal basis? Okay, who thinks AC is a super key? We have more people for a super key. So let me tell you why it's not a minimal basis. A super key is always a set of attributes, right? It's a set of attributes that determines everything. A minimal basis is not a set of attributes, it is a set of functional dependencies. Do you remember? We take a set of functional dependencies, like the one I had. Let me show you. Is it not? Oh, I was on Zoom, that's why. When I was saying we had a minimal basis, is because we took this set of functional dependencies, all of that, and we tidied it up and got a set of functional dependencies. So a minimal basis is a set of functional dependencies, right? So you cannot say that a set of functional dependencies is a super key, but you can also not say that a set of attributes is a minimal basis, right? It's always a set of attributes can be a super key, and a set of functional dependencies can be a minimal basis. Who is with me on that? Right? I'm just rehearsing the material so that it's clear to everybody, right? So it means that now if I come back to this, AC is a super key because it determines A, B, C, D. What would be a minimal basis here, if you want to speak in terms of minimal basis, what would be the minimal basis? It wouldn't be AC because AC is a set of attributes. So what would be a minimal basis that you see on the screen right here? Yes? The three of them. So you say the three of them would be a minimal basis. Anybody else? What would be a minimal basis? Any other ideas? Yes? Just the first two. So you say just the first two would be a minimal basis. Let's do a poll again to see. It's good because it makes you rehearse, right? Who says all three together are a minimal basis? Who says just the first two are a minimal basis? Right, very good. And you change your mind too. Very good. All right. So indeed, the minimal basis, we could take this set of functional dependencies and compute the minimal basis. It means tidying it up. And if we did that, we would remove that, right? We would remove this because it's redundant with this, right? You can derive this one from these two, right? So it would disappear when we compute a minimal basis. So it's not a minimal basis, but this would be a minimal basis, all right? So it allowed us to rehearse a little bit the notion of super key and the notion of minimal basis here, right? All right, but let's come back to AC because AC is a super key, and this is what I wanted to look at here. AC is a super key. Do you agree that the two dependencies that I have above, A determines B and C determines D, who agrees that A alone is not a super key? You agree here? Others? Who agrees that C alone is not a super key? All right. You would not be able to derive A gives you ABCD. You would not be able to derive that C gives you ABCD. In other words, the closure of A is AB, and the closure of C is CD, right? So A and C are on the left-hand side of functional dependencies. These are non-trivial dependencies, right? It's not like we would have A determines A or C determines C, right? They're non-trivial. A determines B, C determines D. And in fact, this is what we want to look at right now for the Boyce code normal form. We actually don't like these functional dependencies. We don't like functional dependencies when the left is not a super key. So we like the third one, we don't like the first two. That is the idea. So for example, I have a table here where we have, that's another example where we have the functional dependency that AC gives you D, right? And the transitive closure would mean that AC gives ACD. So you agree AC is a super key here too, right? Okay. So this here is a case where all functional dependencies have a super key on the left, right? I don't have any functional dependency where the left is not a super key. Who agrees with that? Right? And in fact, this is very good. That we actually like. We actually like it when everything on the left of my functional dependencies is a super key. Right? So the title remained, right? But this is the one with undesirable properties. That is the table with undesirable properties because we have functional dependencies and the left is not a super key. And in fact, that's exactly what the Boyce code normal form is. You have a table in the Boyce code normal form. When you look at the functional dependencies, the left is always a super key. Right? That's the Boyce code normal form. So this table right here that you see on your screen is in the Boyce code normal form because when you look at the functional dependencies, what's on the left is always a super key. I added trivial because we don't care about the trivial ones, right? Where we have A determines A or that kind of things. This, of course, we don't care about. That would always be true, but we don't care about them. They're just trivial. So I really mean the functional dependencies that are non-trivial, that are of interest to us. So this is the Boyce code normal form. Who is with me? Right? We just require that all the left-hand sides of my minimal basis, if you take the minimal basis, all the left-hand sides should be super keys after the tidying up. Okay. Now let's see and work on the intuition. Who agrees that if I have a table with just 2 columns, 2 attributes and nothing else, who would agree that that table will always be in the Boyce code normal form? You agree? So we can do it on a case-by-case basis, basically, in order to see that. What if the super key is AB, right? The only super key of the table is AB. The second case is that we have the functional dependency A determines B, right? Super keys A and AB. Then we have the third case that B determines A, and then the super keys are B or AB. And in the last case, it goes both ways. A determines B and B determines A, right? Who agrees that in all 4 cases, everything is a super key on the left? We never have, in any of these cases, something on the left-hand side of a functional dependency that's not a super key. Who sees it now? Right? So what that tells us is that if we keep decomposing tables to the point that the tables have only 2 attributes, then we're fine, right? There's no more risk anymore that we wouldn't be in the Boyce code normal form. So it's a fun fact to know that if I tell you there's a table with 2 attributes, you don't even need to think or you don't even need to look, right? 2 attributes, it's in the Boyce code normal form anyway, no matter which case we are in, right? These are the 4 possible cases for my table. Okay. Okay. But that was just a fun fact, right? If you just have 2 attributes, then it is in the Boyce code normal form. Now, the goal that we have, since we know about the Boyce code normal form and we know it's a good thing to have a table in the Boyce code normal form, if we take a table that is not in the Boyce code normal form, we would like to decompose it into 2 or more tables that are in the Boyce code normal form. That is our goal, right? So we want to project the table on different subsets of attributes such that we get tables in the Boyce code normal form, right? But there is something important when we do that, is that when I do this decomposition, we should be able to go back the other way around. So we should be able, from the decomposed tables, to reconstruct the original table, right? So what I'm essentially saying when I'm saying that from these 2 tables, we should be able to reconstruct the original table is that the information is the same. The information here should be exactly the same as the information there. We shouldn't lose anything in the process, right? Who is still with me? Right, very good. But then, if I want to decompose a table in Boyce code normal forms, I have a naive idea. What if I just take subsets of 2 attributes, right? I can do it with any table, right? For example, you take a table A, B, C, D, E, F. I can take A, B, B, C, C, D, D, E, and E, F, and I just project over these tables. Why can I say that everything is in the Boyce normal form now? If I decompose in this way, why can I say that this is in the Boyce code normal form, the 3 tables below? It's because of what I just told you 1 minute ago. Yes? Exactly. Exactly. If you have 2 attributes, you're guaranteed to be in the Boyce code normal form. So this is actually an incorrect idea, right? I will tell you why. But in fact, who agrees if we would do this, if we would project into plenty of subsets of just 2 attributes, it seems that we would have solved the problem because all of our tables are in the Boyce code normal form, right? Who sees that? Right? But the key here and the reason why it's not working is that we can't reconstruct when we do that, or we can't always reconstruct. So it might be that when we try to take these 3 tables and reconstruct the original table, we'll get something different. Let me re-ask the question I asked 10 minutes ago when I told you it must be the same, or we must be able to go back. Who could tell me more precisely and formally what it means to reconstruct? When I'm saying we reconstruct the original table from the 3 at the bottom, does anybody see that? What relational algebra operator would we use, more or less, on the bottom tables? There are not so many things we can do with multiple tables, right? Yes? A join, exactly. That is a join. So we basically are looking into a decomposition of that big table on the top into smaller tables, projections, in such a way that if we join them back with natural joins, we get back the table on the top. Who gets that now? Right? So then we can say it's equivalent. If the join of these is the same as this, then we didn't lose any information. We have exactly the same data here and the same data there, right? But the problem is that with this naive apparent solution of just decomposing into tables with 2 columns, if you do the join of this joined with that, you're not going to get back this table. So this doesn't work. This is a bit more complicated than just that, right? So instead, there is an algorithm. There is a way to go in order to find how to decompose the original table. In fact, it's actually logical, because if I tell you that table here is not in Boyce code normal form, what does it mean that a table, what can you say if a table is not in the Boyce code normal form with the functional dependencies? By definition. There is at least one functional dependency such that yes? So that exactly, so that what is not a super key? The left or the right? The left, exactly. So the Boyce code normal form by definition means that all the left-hand sides of your functional dependencies, non-trivial ones, are super keys. So if I have a table that breaks that, then it means that there is a functional dependency such that the left is not a super key, right? Who agrees? Right? If I tell you in a room, all the cats are green, and then you tell me, no, that's not true. It's not true that all the cats are green. Then you can tell me, then it means at least one of the cats is not green, right? You agree with that? It's exactly the same thing here. So since BCNF requires that all the functional dependencies that are non-trivial must have a super key on the left, if I have a table that breaks it, then it means that at least one of the functional dependencies has something on the left that is not a super key, right? So this is what it means. So what we do is that we take such a functional dependency that whose left is not a super key, right? It means it doesn't determine everything. We do compute the closure, so we try to put all the attributes we can on the right. We compute the closure of that thing and add all the attributes we can here. We know in any case that's not going to be everything, right? It's not going to be everything because otherwise it would be a super key. And we said that it's not a super key, right? So it will be some, but not all the attributes. Who is still with me? I'm very careful not to lose you because there's a lot of reasoning in there. So let's say in that case, the closure of A is ACD. So we also add C, right? You agree? A determines C and D. A determines foo and true. B determines foo bar and false. Do you see the functional dependency here in the table? Right? A determines C and D. Who sees it? Right? Very good. So you see it. So, but let me take the example where I just changed the value here and we just had A functionally determines D in that case. All right, so what I do is that everything on the left and on the right is my first projection. That's the first table in my decomposition. I just project on everything that is in here. And the other part is going to be the left-hand side plus the rest. In that case, B and C, right? So basically, the left-hand side is like a pivot, right? The left-hand side is basically the what is in both projections, right? Then the right-hand side would go, the entire closure would go in the first projection, and everything else in here would just go into the second projection, right? Who is following? If I gave you a table not in the Boyce code normal form, and I give you a functional dependency such that the left is not a super key, who would be able to give me the decomposition? Right? Okay, let's do it. Table A, B, C, D, E. A, B, C, D, E, these are my 5 attributes. And I'm giving you the functional dependency. B determines C and E, right? And that's already the closure. So the closure of B is BCE. You agree B is not a super key, right? So what is the decomposition then? Right. So I have the table A, B, C, D, E. And the functional dependency that I don't like is B determines C and E. How do I decompose that table? Yes? B, C, E. Yes, B, C, E, and A, B, D. Who sees that? Who agrees? Right? Everybody? Because I see some people who don't raise their hands. Do you also agree? Who sees it? Who doesn't see it yet? So, and I just repeat just to be absolutely sure. I have a table that is not in the Boyce code normal form. It means I have a non-trivial functional dependency so that the left is not a super key. I compute the closure of that set of attributes that's not a super key and add anything I can on the right from the closure. Then everything together gives me my first decomposition, my first table, my first projection. And for the second projection, I take the left part plus everything that wasn't there in the first one, right? For whom is it clear now? Right? That's how it works, and that is my decomposition. And if I do it now, so I basically project on AD, I get that, right? You agree? And I project on ABC, and I get that. By the way, when you project on AD, you're actually making the functional dependency explicit because you see now that D is a function of A in here, right? So this is what's happening. So now we say we decompose. And what happens next is that we check, are these tables in BCNF? If yes, then we are done. We have found the decomposition of BCNF tables. If not, then we just keep decomposing and decomposing and decomposing. We just iterate and continue and continue. In that case, I can already say the one on the left is BCNF. Why? Yes? Exactly. The one on the left has 2 attributes. So this one we are safe. And the one on the right, you just need to scrutinize maybe a little bit more and see, okay, is that one in BCNF? It looks like it, right? I don't see any functional dependencies in there that would break the BCNF, right? So now I'm done, basically, in that case. And otherwise, I would just continue and decompose further. Now, in order to know whether we've done a good job, we need to compute the join of these 2 tables and see if we get back to the original table, right? Do you agree we do? Who agrees that this is the join, that it matches? Right? The join of the 2 tables at the bottom corresponds to what we have on the top. In fact, that's always going to be the case. And it was the case because we were very careful in the way we projected. We were very careful in the way we decompose because we started with a functional dependency. We knew that A was determining D when we did that, right? And so this is why, in fact, it all works and the join gives us back the table. And so when we do that, basically, what we're saying is, okay, is the first table, we forget about it. We don't want it. It's not BCNF. That doesn't fulfill our criteria. And we replace it with the 2 tables that are below because these are in BCNF. That's the essence of what we are doing. And so generally, there is a method to ask if when we join these 2 tables back, we get R. And that's called the chase algorithm. It's one of the classics that we teach on in computer science curricula. That's basically a test. It's a test of whether or not the join gives you the original table back. And the way you ask whether or not the join corresponds is basically, you agree a table is a set of tuples, right? So when you ask, are 2 tables the same? Meaning, is the original table the same as the join of the other tables? I'm asking if two sets are the same, two sets of records. And so when I want to show that two sets are the same, what do I do in mathematics when I show the inclusion in both directions, right? If I want to see that, to show that A equals B, two sets, the set A equals the set B, I show that A is included in B and that B is included in A, right? Who agrees? Right? It's just a set theory. Well, in fact, there is one direction in here that is trivial. It means that if you take a record or a tuple or a row or a map in the original table, then it has to be in the join. That one is just by construction, right? Because if you take a tuple A, B, C, D, let's take that tuple. The projection of it on the first table will be AB, small a, small b. The projection on the right will be ABC. And then when you join them back, then AD, sorry, will match with ABC, and that gives you back that tuple also in the join, right? So if you take any tuple in the original table, it has to be in the join as well, right? So it means that the join can only be bigger, right? If you messed up the decomposition, you can get a join that is too big, but you can't get a join that is too small, right? Who is with me? Right? So the risk is that when you decompose, the join gives you an enormous table with just too much garbage, data that's not supposed to be here. So it's the other direction that's actually complicated. When you ask if you take a tuple in the join, is it in the original relation? That is the one that is a bit more complex to do. And so the way it's done is the chase algorithm. So basically, let's take a tuple in the join. So let's assume that this green, the small a, small b, small c, small d here, let's assume it's in the join. Well, if it's in the join of this, then it must come from somewhere, right? Because the join is made of combinations of tuples. So if I have this in the join, it means I have to have had AD in the table on the left, and I have to have had ABC in the table on the right, right? That's just the definition of the join. Who agrees? Right? Okay. Now what we know from this is that this was obtained by a projection from the original table, right? So it means that I have AD and something else, right? That's what got projected to AD. The other one here, ABC, was projected from the original table to ABC. So it must also come from somewhere. It must come from some tuple that had ABC and then whatever, right? Who agrees with me, right? So I have to have something like this in the original table, such that this got projected to AD, this got projected to ABC, and then the two got joined to ABCD, right? So far, so good? Okay. Now, do you remember that I had the functional dependency A determines D, right? That's the reason why we decomposed it in this way, right? Because I had A determines D. Now, if you look at this table in yellow that has missing pieces in there, and I tell you there is a functional dependency that A determines D. Can you add more things to that table? It's like solving a Sudoku or a table, right? So I'll give you the break to think about that, if you can fill some of the blanks in there, and then conclude something. So let me grab some coffee, and I'll see you in 15 minutes, right? Oh, just before I ask, just to know, because I'm trying to decipher your faces. Who thinks I'm too fast? Who thinks I'm too slow? Okay, who thinks I'm at the right pace? Okay, very good. So I'll continue at the right pace. Thank you.